Hey guys, today we're going to go ahead and discuss the concept of calorimetry. And calorimetry is a technique that we're going to use a lot this year to be able to measure the conversion of energy, but also the transfer of energy. And so we're going to focus today on the technique. We're going to focus today on discussing the system and the surrounding concept. And we're also going to go ahead and focus on what is calorimetry as a concept and why do we do it. We're going to start by defining system and surrounding. A system is going to be either chemical or a substance that we are going to be examining the nature of, the energetic nature of. Now, the system can undergo a physical change, i.e. like melting or freezing, or it can undergo a chemical change through the course of a chemical reaction. In each of these circumstances, the system is going to be changing in its potential energy. Now, the surroundings is anything around the system that is going to be changing in its kinetic energy. So this would be the area or the region or the substances that are absorbing or releasing any energy that's either going into or coming out of the system. So again, system is going to be mostly changing in potential energy, whereas the surrounding we're going to talk about in changing in kinetic energy. Now, temperature, remember, is a measure of kinetic energy or average kinetic energy. So if the change in temperature is a representation of the change in the average kinetic energy. So if the average kinetic energy is changing, there has to be a reason. Energy must be conserved. So if the average kinetic energy of the substance we're looking at is going up, that energy must have come from somewhere. If the average kinetic energy of a substance is going down, then that energy must have gone somewhere. So we use calorimetry to determine quantitatively how much energy is being transferred into or out of our system and surrounding. One of the most important things to realize when we're talking calorimetry is that we do these experiments using a calorimeter. Now, calorimeter is constructed from a couple of different components. We're going to focus in this class on experiments in coffee cup calorimeters, which are the most rudimentary, basic type of calorimeter, but there are others. There are things called bomb calorimeters out there, which we won't get into too much. But at the same time, we need to understand that all calorimeters are built in the same way. They are an insulated device that is used to capture or provide energy into a system. So if a system is going to release energy, then the surroundings in the calorimeter are going to be absorbing the energy released by the system. In doing so, the temperature of the calorimeter is going to change. The temperature change of the calorimeter represents the change in kinetic energy of the calorimeter, and the change in kinetic energy of the calorimeter is going to represent the change in energy of the system, but in the opposite direction. So if the system loses energy, the calorimeter gains it. If the system gains energy, the calorimeter loses it. In a calorimeter, there are a couple of key aspects that are very critical. First of all, it needs to be well insulated. If the calorimeter can lose energy beyond it into the environment around it, it's not going to be precise. Secondly, in a calorimeter, we need to assume the energy is transferred throughout the entire calorimeter. So what we need to do is continuously stir the calorimeter's content. So in most cases, we're talking about water, but in some of the fancier calorimeters, you can even do antifreeze or glycol or other chemical compounds that can be used that change temperature in different ways. One other thing that we want to do in a calorimeter is ensure that we're maintaining a constant pressure. Now, in our coffee cup calorimeters, that's not really too much of a problem, but in bomb calorimeters, oftentimes that can be challenging because as the temperature changes, so does the pressure of certain gases. We're going to talk about that later when we get to gas laws. But just be aware that in constant pressure calorimetry, we're going to be observing all of these chemical and physical changes simply using a constant pressure of gas around the calorimeter. Now, there's really only one major calculation that goes into calorimetry, and it's centered around the equation Q equals mc delta T. Now, in future videos, we're going to do a lot more of these calculations, but let's go ahead and talk about this equation briefly as a concept of what are the variables. So Q represents heat, M is the mass of the substance, C is the specific heat capacity of the substance, and specific heat is the energy necessary to raise 1 gram of a substance by 1 degree Celsius, or 1 Kelvin. and delta T represents the change in temperature. Now, I've already mentioned specific heat capacity. Specific heat capacity, remember, is the energy it takes to change 1 gram of a substance by 1 degree Celsius. There is something also called heat capacity. And the heat capacity is, well, let's ignore how much there is. And we'll just say, in this thing, how much energy did it take to raise that whole thing by 1 degree Celsius? In other words, we just remove the gram aspect. So specific heat is an intensive property. It doesn't matter how much of the stuff you have. But heat capacity is an extensive property. For instance, if I have 1 gram of a substance versus 100 grams of the substance, the specific heat is going to be the same, but the heat capacity of the 100 gram sample is going to be much greater than the 1 gram sample. Another thing to be aware of is the specific heat capacity for water. It's one that we're going to use a lot this year. So the specific heat capacity of water is 4.184 joules per gram degree Celsius or joules per gram Kelvin. What this tells you is that it takes 4.184 joules to raise 1 gram of water or 1 milliliter of water by 1 degree Celsius. So let's take a look at a practice problem similar to one that you might see regarding calorimetry. Now in this case, we're going to go purely qualitative. We're not going to look at any numbers. We're just going to look at a system and surrounding and try to figure things out regarding that system and the surrounding. So I have a titration reaction, which is a neutralization of sodium hydroxide with hydrochloric acid. Now, as I'm performing this, realizing that the beaker in which I'm performing it starts to feel warm. Okay? So, a couple of questions. First of all, what is the system? Secondly, what therefore would be the surroundings? Third, can you tell me the direction, the relative direction that heat is moving? All right, so again, thinking of system to surrounding or surrounding to system, all right, which direction is the energy moving or the heat moving? And finally, is the reaction itself endothermic or is it exothermic? So let's go through each of these. First of all, what is the system? Now, if you remember back to what I said earlier, the system is a change in potential energy. Potential energy in this case is changing over the course of the chemical reaction between the sodium hydroxide and the hydrochloric acid. So the system in this circumstance is going to be the actual interactions, the chemical interactions between the hydrogen ions and the hydroxide ions, as well as any interactions that are occurring between the sodium ions and the chloride ions. Now, if you think about a net ionic equation, the only thing that's really happening here is that we have a hydrogen ion combining with a hydroxide ion to form water. So bonds are forming there. So the system itself is the formation of bonds from H plus and OH minus to H2O. Remember, the sodium and the chloride in this case are both going to be spectators. They're aqueous in all circumstances, and they're going to be spectators in the system. So really, it's just the water formation from the H plus and OH minus ions. That's our system. The surroundings. Now, this is tricky because, believe it or not, the surroundings, if you remember, being anything that changes kinetic energy, well, that involves everything in the beaker. And the beaker includes both the water, but also all those ions that we just added. So even though we look at those ions and the water molecules as the system, they, as a system, are also going to be changing in their kinetic energy. So the system aspect is any change in potential energy. But the surroundings, we have to account for the HCl and NaOH as well as the water, because all of it is a part of the surroundings. So again, the key here, you have to keep this straight in your head. System, change in potential energy. Surroundings, change in kinetic energy. Okay? The next part of the question is, which direction is the heat traveling, or where are we moving our energy from and to? Remember, energy is conserved. So there's no change in total energy. It's just a matter of what's the form of the energy and where is it coming from and going to. Well, the beaker heated up. That tells me that the beaker and all of the contents within the beaker gained kinetic energy. So if it's gaining kinetic energy, that means that the system itself must have been providing the energy into its surroundings. Otherwise, the surroundings wouldn't have increased in kinetic energy. So the system is going to lose potential energy, and the surroundings is going to gain kinetic energy. This process, in part D, you'll recognize as being exothermic in nature. So the exothermic nature of this reaction leads to an increase in temperature of the surroundings, which is the beaker and the solution within it. So that wraps up today's video. Today we talked about not just what is calorimetry, but how do you construct a calorimeter and how do you define the system and the surroundings in the calorimetry type problems. Remember, system and surroundings are going to be predicated on the type of energy that's changing, whether it's potential energy for a system or kinetic energy for the surroundings. Changes in kinetic energy, remember, can be calculated using the Q equals mc delta T equation. We're going to go further into that in the next video. I'd like to thank Annie Lee and Hannah Stairs for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one. And so today what we're going to talk about is the idea of system versus surrounding, and as well. Dang it. Now this chemical reaction is exothermic in nature, and when you perform this, you'll recognize, or is that actually part of the, dang it! Yeah. Sorry, I didn't look at D. Dang it, sorry. It's okay. We good.